Today we're going to do a training on the various interactions of GTS and X with other programs, mainly AutoCAD, but we'll also look at one of the cases where we import a full structure as well, not just other geometries. And the main goal being that what we're going to see is the interaction between what's a tunnel excavation and the piles of this foundation with a structure in place and the soil. So we will cover three different parts in this training. Part one will focus on interaction with AutoCAD and Excel in order to generate a 3D terrain. So we'll be importing DXF files for topography, and we'll be importing boring hole data from Excel, and we'll use that to create the 3D terrain. And then we'll export that back to AutoCAD just to show some of these interactions. Second part, we'll be importing a solid tunnel from AutoCAD. What will be a file that we actually just found on a database online. It's a .sat file. We'll be importing that, and then we'll also import the terrain, the 3D terrain that we generated in a previous stage. And we'll actually also include a raft. There won't be a building. In part two, what we'll do is we'll simulate the building using point loads, which will be imported from an Excel table. And then the last part, part three, we'll be doing a full import of a building, and then we'll import the geometry of the terrain with the tunnel. And in that stage, in this case, we'll actually model the excavation of the tunnel, the construction process, and we'll do a comparison between the building and the raft with piles versus no piles. We want to see the settlement between these two due to the excavation of the tunnel nearby. So that's kind of the sequence we'll follow, and the focus of the interactions will be these three programs, AutoCAD, Excel, and Gen. But we have shown in the past, and it is possible to also, for GTS and X, to interact with our MIDAS Civil software, which is specific for bridges, and our MIDAS SoilWorks software, which is also geotech, but it's actually 2D and conventional methods. So we can go ahead and get started. On the first part, as I mentioned, what we want to show is the capabilities of the program to allow you to generate a 3D terrain based on data from the field. So you can have an AutoCAD file, DXF contour lines, and bring those in, and we have a tool to generate the plane based on that surface contour, like the topography plane. And then you can also have data from boring holes that you can put into a simple Excel table, and you can bring that in so you can create the stratus and use that to generate the whole model in 3D in very simple steps. So firstly, I'll be opening the file in AutoCAD just to show you a few pointers on how to make sure your file is able to be imported into GTS and X without any issues. The first one, and very common, is that you should be by the origin. The geometry should be relocated if it's not, to be right by the origin, the coordinate 0, 0, 0. That's very important for it to be able to import to GTS. And the other is that all the geometries, all the contour lines, it doesn't matter if they're in different layers, as you can kind of see there in the colors, but they should all be polyline. Let me open here. So this is the file we're going to import for this first part. You can see that they're just simple contour lines. But if I leave my cursor, so for instance, this is in one layer called 7111, but it's a polyline. And if I go to another, this pink line, this would be in a different layer, but it's also a polyline. So just keeping track, the program will recognize the different layers and will group them for you accordingly. All that matters is that you're close to the center and that you were using polylines. Here we have additionally drawn in some circles that represent the location of where the boring holes were taken relative to the 3D surface, the 3D topography. So this is just a plain, simple DXF file. When you are gonna save it, you can actually even save it as a DWG or as just a DXF. It doesn't really matter for GTS and X. You can import both methods. And it doesn't really matter. I mean, save it in the latest, I suppose, but it doesn't really matter which version you save it in. So what I'm going to do now from now on is kind of skip back and forth between the presentation and the program because I'm going to show you the steps directly in the software. So what we're going to do now is import this 3D DXF that we just showed you on AutoCAD. So here's GTS and X. What we want to point out immediately also is once you start a new file, a new program, you'll have the option of selecting if you're working in 3D, in 2D, or you're doing an axisymmetric, and you'll have the unit system. This is a global unit system, which you can change down here at any point, even after you run the model. However, this unit system is for the, I guess, analysis, if you will. It's the global unit system, but we can actually also have to keep track of the unit system we're using when we're importing geometries, and that's actually done over here in Tools, Options, Geometry, Import. In this unit system, in this case it's meters, but we're going to see in part 2 how we have to modify this if something's not properly scaled in AutoCAD, since AutoCAD is unitless. So we'll go here to Import DXF 3D, and we'll find what is that DXF file, the boring DXF file. So we see here it's imported all the lines. If we go to the workstream geometry, it's actually grouped them into the layers that we had seen. So I'm deactivating the contour lines first, and what I want to do initially actually is, I'm going to drag this to the side, is actually show you how to generate the strata with these boring hole data. So we have this tool called bedding plane, and this allows you to say like how many planes you have, and what you can do is tell it by location. For instance, at this, either coordinate, manually type it in, or this is where drawing these in is handy. You can tell it at this location, the first plane is at this depth, the second plane is at the, such and such depth, and so on and so forth, and you would continue going one by one, adding this data. Well, you can also do, the program allows you to import directly, is a table from Excel. And so you would basically be doing kind of like the same information. You would give it location of each specific boring hole, and then you would give it the depth of the planes that you found for each one. And the units are, of course, important to keep track of. So here we're in meters. And so the program allows you to just directly import that table. So it kind of saves you a little bit of the headache of manually doing this, although you can also just verify this. And here what you want to do is just give it dimensions of the planes that are going to be created. So we're telling them, based on this information, make me planes of 200 by 200, as we can see there. So this is part 1 of the terrain we're making, which is the strata. And now we want to go back and use this information for the topography. So you can see how those boring hole data is actually useful, since everything's going to line up nicely because that data was taken into account or drawn into the AutoCAD. So for the topography, we're going to use this subroutine or submodule, if you will, called Terrain Geometry Maker. So I'm going to click on the first part of it. And it's going to open this new window, almost like its own little program. And we're going to go here to import DXF file. This one actually has to be DXF. And what we see here are the different layers. In this case, we want to keep the visible layers of the contour lines, which I guess I could have named it better. I just know they're the ones that are with the 7,000 in them. And we see here the side view and the top view. I'm going to click inside of the top view, and these icons are going to turn on. What we want is the one that's called Terrain Geometry. It's a little hammer. And this is what's going to allow us to select the lines that we want, the contours that we want, and give it dimensions for the geometry rectangle it's going to make, or plane it's going to make. So we just select all of them, and basically here I just select 2 corners. So I click inside the number, I click on this arrow, and then I click on a corner. And now I can, given the 2 corners, I give it plot zone. So we see there that's a plane that's going to be made out of these contours. And here the number of sampling points, the more sampling points you give it, the more accurate it's going to be. So we can just say something like the range is 2 to 200. So 40 is sufficient for this case. And we see here if I rotate it, it's actually pretty accurate in terms of what the deformations of the geography is, topography. So I would just go here now to export surface. In order for the program to read it in GTS and X, it has to be exported back, not saved. You can save it and then it'll open back into this program, but you need to export it to this format, TMS, in order for it to be readable or imported into GTS and X. So we generate this, we export it back, and now we go here into GTS and X and go to import TMS, and this is basically the file we just created. So now we have our planes of the topography and the strata, and we can proceed to use this to divide a solid geometry in order to get our block or our final geometry. So I'm going to use 3D Box, and the reason that I use 3D Box is the program has a feature that can automatically apply boundary conditions for you once you've meshed everything, but the side faces have to be completely vertical, and the bottom face has to be completely flat or horizontal. So this is why it's very recommended that you use kind of these approaches where you have some sort of huge or a box or a rectangle as your initial geometry and you use planes to divide it. You can do it, irregular geometries. You would just have to manually select the faces, the nodes to apply the boundary condition. But if you want to use the auto feature, then your model has to be a certain shape as far as the boundaries go. So this is why I'm using the cube. So here I'm giving it dimensions and locations. Of course, I already know. I can go here to preview, and I already know more or less what the dimensions need to be and where the origin needs to be. The point being that the cube has to fit inside all of the planes. So we see here that these two are not exactly lined up, but the cube does have to fall in between all of them, since I'm going to use the planes to divide the cube or the solid, and the solid the plane has to go completely through the solid in order for it to be able to divide it. So here I'm just kind of giving it some different inspections. We see that the planes go through it all different sides, just making sure so I can use these like kind of settings to give me a better idea. Everything looks fine here. And if I apply it, we can see that all the planes go all the way through, but in this one, it kind of cuts it close for some of them. So that's why it's important to inspect beforehand, since I wouldn't be able to divide if it didn't go all the way. So now I can go here to divide, solid is the target, and the planes are the surfaces, the tools. And I can just get rid of by clicking on it and either going to the right, delete, or just clicking delete on my keyboard. And this is the terrain that we want to retain. I'm going to select everything and just give it here another right click and go to a random color just to make it a little more clear. So this is like our starting point of geometry. You can then export this back to AutoCAD if you wanted to. You can export this CAD file as a parasolid, and our AutoCAD can actually read that file. So if you had different teams, you can use some of these features of the program for generating the 3D terrain that might be a little more complicated. This is the parasolid file that we just exported. You could send it back to AutoCAD and send it to another team, and they could use this. It might have been a little trickier to do it within the tools of AutoCAD, but this can be like their starting point or the sharing file, and then you can actually make new changes to the geometry here in AutoCAD and send them back to GTS and X. or you can just do your modifications, similar commands to AutoCAD, all within GTS and X. So this is part 1. Hold on. So this is the parts that we were doing. We imported the terrain and the topography, and we divided it. And then we're showing that you can send it back to AutoCAD if you needed to make some modifications. In this case, for part 2, we're gonna just import this 3D CAD file. And they made a few changes. What they did is they cut out an area of where the raft and eventually the building's gonna be. So for part 2, what we're gonna do is we're gonna import this 3D tunnel. It's a solid tunnel. And then we're also going to import this modified terrain, and combine it all, mesh it, and then we're going to not include the building yet. For the second part, what we're going to do is we're going to simulate the building as point loads, and these loads are just going to be imported from an Excel table. And the main focus will be to study how it's affecting the tunnel, basically how the tunnel fails. And just as a note, this tunnel file was actually just from an online database of CAD files. So we'll be importing this. It's a .sat file. It's an AutoCAD file. And I'm going to go back to the program just to kick it off from there. So we'll start here, a new file, 3D. So something that I did notice, however, I found, as I mentioned, this CAD file of the tunnel in a database online, but the dimensions were very large. So what I had to do in order for it to match was actually change this to millimeters in terms of units to be imported. And now I can import this SAT file. We see here we have different options. We can do IGS. I can show you an example of that real quick if you want, just to show. This is not really part of the tutorial, just showing you that we have different kinds of solid geometries you can import. It'll just take a sec. So the handy thing about this is, in many cases, you can skip the whole learning how to model in GTS and just bring in, these more advanced geometries that we see here as solids, and you can go straight into connecting it to the soil and meshing instead of having to do that, all within the program. So in most companies, you have a very specific role, and you might have somebody that's really good at AutoCAD that can do all this for you, and the geotech engineer can just focus on the meshing aspect. So here, that was just showing a IGS file. The tunnel we're actually going to be doing is a .sat file. And here we go. Similar to the rule for the terrain that we imported, you want it to be in the origin. And so you notice that the dimensions that I had when I imported it were millimetric, but if I measure the dimensions of this tunnel, it's still it's almost 300 meters long. So had I not changed the import units, it would be 1,000 times bigger. So you have to kind of keep in track. Sometimes when they make the files in AutoCAD, they don't keep in mind what dimensions you needed them in or you're going to be working on, so you can modify that before you import a file. So here I went back to meters, and now I'm going to import the terrain, which is a parasolid. And so we go from here now. We basically can see how it can become very handy with these features for a GeoCAD engineer to get almost like halfway through the project just by importing files. So what I'm going to do now is I'm going to first move my tunnel into its final position, and then I'm going to divide it. So I'm going to go here to geometry. Actually, I'm just going to change the view and go here to geometry, translate. I'm just going to draw a rectangle over the solids of the tunnel. I see I captured everything there. In terms of direction, I'm going to select the Z axis and I'm going to tell it just negative 30, positive is up. And I'm going to tell it to move it. And I can preview it there. So now the tunnel, let's say it's in its final place. What I'm going to do now is I need to divide the tunnel into, these parts that are extruding out that I don't want. So I'm going to draw some planes that cover the tunnel only and divide the tunnel by those planes. In order for me to draw that, I need to move this work grid, since that's where I can draw my basic geometries. I need to move that work plane to the face, to the side face of my terrain. So for that, I can go here, move work plane, and there's different methods to do this. I'm just going to select the 3-point option, and that allows me to just select 3 corners of the face that I want the plane to line up with. So we see it there that now if I draw something, it'll be directly on the same face or plane as the face of the geometry. So now I can go here to rectangle. I'm going to draw a rectangle but make it a face, kind of like what we did with the terrain, so that I can divide the solid by it. In this part, it doesn't really matter the dimensions so long as it covers the entire tunnel, since I'm going to be dividing this tunnel by that. So it just needs to cover it entirely. And what I want to do is I want to make a copy of that to be on the other side, since I need to divide the tunnel on both faces. I no longer need this work grid. What I can do now is go here to translate and make a copy of this geometry. And in terms of direction, I could tell it select the direction and tell it a distance. If I don't know, let's say, the exact distance between where I want to move something, I can use this other function called 2-point vector. So I can tell it a starting point, which is this face, and an ending point, which is basically at the end of my model, and it'll calculate it for me on its own. And I can kind of preview it, and that's exactly what I want. So now I have 2 faces, and I can divide the tunnel. So here I'm just selecting the geometries that are not going to be part of the division, and I can right-click and just tell it to hide them. And I can go ahead and do this similar to what we did with the cube, is divide a solid. I find it easier to, since there are actually, this tunnel, this AutoCAD file that I have found is actually composed of several rings and a few other geometries inside. So it's easier just to select everything by going to the front face and drawing a small square. And then the tools are these 2 planes. And we see here now if I draw a square, there's 2 sections there, and I can also draw a square there, right-click, and delete these parts. And so here, if I give these random colors by right-clicking, it'll give you a better idea of, that we're talking about different layers. Even though they're solid, it's a pretty, pretty detailed tunnel, actually. I noticed that even inside there's some specific geometries. I don't really know what that's supposed to be, but we're going to keep it and mesh it all just to, it won't really affect the results, but we just want to show how strong the mesher is for GTS, that even these kind of very detailed small geometries the program can handle. So now we can activate the terrain back, and we want to do is connect everything. So we could do this through a series of iterations of doing this embed, and telling the program that I want to embed the tunnel into this layer and then embed the tunnel into that layer. Or we can use this function called AutoConnect and use the Boolean method and just select everything over here. Just go to apply. Now, in some cases where there's several layered solids, like we have for this tunnel, since the tunnel itself is almost composed of three rings, if you will, we have to verify that all the layers connected, and if they didn't, we can just repeat this process just in case. So now we can kind of see that the tunnel has gone through. Visually, we have this tool called here, check duplicates, that will light up in orange the faces that are being shared. It's a program basically recognizing contact. So we see that there are some, the faces are orange between the layers, the raft, and you can see that the layers are orange for some parts of the tunnel, but you can actually kind of catch near this edge and near this edge that it's clear that it's somehow only the inner tunnel is lighting up in orange, but not this outer tunnel. So we have to do, in this case, the auto connect one more time. So I'm just going to select everything again. I already had this open, and I'm just going to apply it one more time. And so now if we check again the duplicates, we should see that there's an additional orange. Now you can kind of see that there's a new kind of layer in orange that we hadn't seen before. So now everything is connected. So it takes a little bit of practice, but you should always check the duplicates before you start meshing, just to make sure that everything is properly connected and you don't get it to the end, like when you're running finally the model, to find that something is not meshed properly. So now we can proceed to meshing. And in this case, what we want to do before you mesh is actually define the materials. So we go to this new tab here, mesh. This is where you define your materials. You would go to create, and we have a long list of materials under isotropic. We have a few for rocks under orthotropic. We have special curves that you can use for 2D linear equivalent, and then your interfaces. So you go to isotropic, you select from the list whatever behavior constitutive model you want to capture, behavior of the soil you want to capture. You see we have some pretty advanced ones like the hardening soil, small strain, some other ones for rock like the generalized soap brown. We also have the modified chem clay or soft soil creep. So there's several. For this case, we're kind of sticking with more column, which is a pretty common. So let's say you define the material and you would repeat this process for all your different layers, and then you go to property and tell the program how these materials are going to be used. So you would have a material for, let's say, if you had piles, steel piles, you would tell them, all right, so the steel pile is going to be a 1D element, and then you have all these other materials that are going to be for your, let's say, rock layers or your soil layers. So you make them for a 3D, and you just match the name of the property to a material you're given so you can keep track of that. So that's the regular process of how you would go about it. What you can also do is you can import tables from Excel, kind of like your own database of materials. We actually have a database internally as well that you can select materials from. Or what you could also do is import the property, which in a sense will bring in the material as well from other files. So what I can do here is just go to the final file that will be included in the tutorial and just bring in all the materials that were used for that file. And so we see here that everything here is just going to be 3D solids, since even our tunnel is a solid. And that bringing in those properties brings in the materials as well. What I do want to show you is the concrete material. We're using this constitutive model called Tresca, and the nonlinear behavior of that, this will be the concrete, we can actually give it a max yield stress. And so what we'll see is that there's going to be parts of the tunnel that exceed these stresses, and that will be shown in the post processor as a failure, if you will, of the structural component. So this is how we can model kind of or test if a tunnel reinforcement is enough or not using these kind of constitutive models. So we can proceed here to start meshing. I'm gonna go here to generate 3D, and I'm gonna first mesh the slab or the raft. I'm gonna give it a size of 5. That's a node every 5 meters. If I do here preview, you can kind of see those red dots of the node distribution. And the material will be concrete. So this is the raft. I'm going to stop and show something else here. For the raft, if I activate the node number, you can kind of see there all the elements that were created and each individual node number. The nice feature that GTS NX has as well is that it allows you to import or apply loads based on these node numbers. So if you're working with a structural team and you both have like the same dimensions, you both agree on the dimensions of the raft, it's much easier using this feature because you can just send them a screenshot showing the numbers of the nodes, and they could create this kind of table where all they have to do is specify the node number and basically the load and the direction of it. So these are kilonewtons, these are point forces, vertical point forces, and the program allows you to directly import that Excel table. And you can kind of visualize that there now, where the basically point loads are being applied. So of course the nodes have to match, but you can easily, I think, do this, or it's easier than trying to do it by a coordinate system, a three-dimensional coordinate system of where something is supposed to be applied. You could of course just manually apply these as well. The geotech engineer could go one by one and apply these by just clicking. But just showing you some of these versatilities that we have. Excel is one of the main programs that we're very compatible or very handy with in terms of these loads, and then later we'll see in terms of graphing results. So we have the raft meshed, and now we're going to mesh the tunnel. I'm going to go back and deactivate these layers just to make it easier. Just right-click and hide. And also for this stage, part 2, we're not going to model the process of excavation. We're just going to model a nonlinear static analysis. So I don't need to have these inner soil layers meshed. We're just going to have the tunnel in place. So I can hide them by just kind of clicking on them, and since we go through different layers, it's going to be different sets of these excavations. So we just want the solid of the tunnel when we mesh. We're not going to bother meshing the inside of what's going to be excavated technically anyways. In the third part of this tutorial, we'll go through the excavation construction process. For this case, we'll just keep it a static case, like if the tunnel was already finalized. So we're going to go to 3D generate, and we're going to select everything. I'm going to give it a size of 1, and this will be the concrete, and this will be my tunnel under name. And it's gonna, when you have many geometries, it meshes in parallel, so you see this kind of bar as it's going through. And so you can kind of appreciate a little more now that this solid tunnel is composed of a few rings. And even though, again, I don't know what these geometries are, I don't think they contribute necessarily to anything, but mostly, I found this CAD file online, but just to show the versatility, the strength of this program in terms of meshing these very detailed advanced geometries. So this is what has allowed many of our clients to do very close to realistic projects for subway stations or for any kind of structure where in other programs you have to assume very general geometries. We have this really strong mesher that allows you to have all these details if you really needed them in place. So we've done the tunnel, and we can now proceed to mesh the soil layers. So this is top. I'm going to give it a size of 10. The material is topsoil. And we can see here that gradual change in mesh size since the tunnel was a node every 1 meter. So the program automatically does this for us since it's properly connected. If it wasn't, then you would just see like a uniform mesh and something would be off. So now we can mesh the next layer, which would be like let's just call it the mid layer 1. And the material is mid soil. The next layer, this would be weathered rock, and I'll just call it like the mid layer 2 or whatever names you want to keep track of your layers. And then this would be the soft rock material. We just call it the base or the bedrock or whatever. So you're just giving them names so you can keep track of the sets. So if we're done with meshing all the geometries, we can now proceed to apply boundary conditions. So here I'm going to go to the tab Static Slope Analysis, Boundary, Constraint. And so here you could manually select the nodes and manually restrict degrees of freedom. But as I mentioned, we have this nice feature so long as the borders of your model, like I said, the lateral faces are completely vertical and the base is completely horizontal, the program will automatically restrain the correct degree of freedom. For instance, here you can see the icon, it's restricting only the degree of freedom in the Y, whereas in the base it's restricting XYZ. So the program will do this for you automatically. And so this is why it's handy to, when you're modeling, to keep these like divisions vertical completely or try to use these square geometries for the border. So now we can go ahead and create our analysis case. We're just going to run a nonlinear static. And since we didn't model the soil that needed to be excavated inside the tunnel, everything is just in place. We can just kind of activate everything. We want all the tunnel sections, all the soil layers, and all the loads to be considered. And what we can also activate here, some other features in analysis control, if you want to consider the K-naught condition, estimate initial stresses. Here's where you can define the water level. This is a global height. So in this particular case, we're also activating the pressure automatically considering it. In this particular case, the raft was at 0. You can see here the origin. So we're just kind of lowering it down a little bit. And so one last inspection. Well, I think actually we imported forces, but we didn't apply gravity, self-weight. So one last thing is just to go here to load, self-weight, and I wouldn't have to be modify the analysis case if I just added to the same load set that's already activated. I could give it a different name and just go back and activate it in the analysis case. In this, we're not doing construction stages, so it doesn't really matter if they're in the same load set. So I'm just going to leave it in there. And that's already being considered in the analysis case. It's right here. So I can just run this model. And for time's sake, since we still have another part of the model to go through, I'll just open one that's already finished. The colors are a little different, but here, the model finishes running. We're now in the post processor, and we can go to this workstream results. We just ran a nonlinear static. So we can see here results like displacements. We can do like a cut, add different slices in different planes using this slice clipping plane feature. And so if you add multiple ones, you can kind of do these kind of things where you can play with it and see results differently. You can also just isolate sets. Since we have the tunnel as 3D, we can just get rid of, for instance, the soil layers and only leave the tunnel on, the sets for the tunnel, and the results will only be relevant to that. So let's go to solid stresses. We were looking at, when we were defining the material, then we gave it like a yield stress limit. So if we go to our stresses for von Mises, we see here that the upper limit is actually that material. It's based on the material that we gave it, that limit we gave it in the material case. So a good part of the tunnel being in red has exceeded this limit, and only some parts of the tunnel are fine. So if we compare this to the plastic status, it's going to match up exactly. And here the red being that we've experienced a plasticity or failure of the material. So this is how we can do one of these studies for how tunnel is going to be holding up based on the reinforcement. In this case, of course, we would have to reinforce the tunnel or use stronger material, or if you will. So this would be the conclusion of part 2. Let's see where we are in the PPT. So we went through this process, meshed, we looked at the results, displacements, and then the inspection of the tunnel. So now we can go to part 3. In this case, we're not going to model the structure as point loads, but we're actually going to bring in the full structure from our MIDAS Gen software. And then we're going to combine that with the geometry. In this case, the tunnel won't be the same 3D tunnel that we did. We want to show the versatility, and the program also allows you to model tunnels as 2D shell elements, which can be, I guess, handy in some respects in terms of some of the results you can see. So we'll be modeling the tunnel, and in this case, we're actually going to see the excavation stages. We're going to excavate the tunnel in 5 sequences. And what we'll be doing is this building will have also piles included. And we'll do a comparative study. We'll do 2 cases. Everything else will be the same, except in one case we'll have the piles, in another case we won't. And we can kind of see how, using Excel or the internal graphing capability of the program, we can compare it differentially, kind of, if you will, design the foundation to not allow it to exceed a certain limit of settlement based on this new consideration. Or it could just be, if it's an urban project, they want to make sure that this new excavation is not affecting the structure too much, if there needs to be some sort of additional consideration or reinforcement, that kind of thing. So it's very handy to use these kind of interactions, because when you do point loads, you can consider really the stiffness or the redistribution in the structure. So what we're going to do is we're going to open the MIDAS Gen, the structural program, and then export it in the, basically what it does is it creates this text file that can be read by GTS and X. And then that text file can be then imported to GTS. We import the geometry, and we do a few commands just to make sure that everything is connected before we start meshing. So I'll briefly open our structural program. This is MIDAS Gen. This is a tutorial for a steel structure. In this case, they fixed the notes of the base. And so we're looking at results here for, I think, settlement or just displacements under self-weight. But I mean, we can see some other results here for different load cases. And this program is actually very good in how it gives you your results. For instance, the axial forces diagrams or moments. It also has some very strong design features for any material, be it steel or concrete. You can design the reinforcement, or you can get like a report for optimal steel section you should be using. Anywho, so here what we would do is just export this as an MXT format file. And as I mentioned, what that would create is, let me find it here, is a text file. It would create this kind of text file with all the information of all the sections, loads, basically the structure. So we're gonna go back to GTS and import this. So I'm gonna go here to new. import MXT. Here's my steel structure. And as I mentioned, in the structural program, they just fixed the base as the boundary condition. We're not going to do that. We're going to basically just connect it to the raft, and the raft will be connected to 3D elements of soil, so it's a lot more realistic. But of course, what we know is that what we care about in this case is what's going to be happening is there's going to be an excavation nearby. So we want to see kind of the, not so much the settlement because of the loads of the building, but because of what's happening in the surrounding soil. But this can also be very useful if you're doing some sort of soil structure interaction analysis with a seismic, load of time history analysis. So we have the structure in place, and now we can import the terrain. I'm just going to double check that my import units are in meters. Okay. So I can go here to import CAD. This is a parasolid. So in this terrain, because we're cutting it a little short on time, as I mentioned, we already had the tunnel in place. I'll show you that real quick. This time the tunnel was made very simply within the program. All I did was draw this on the side using this tunnel section. That was basically a line geometry. And then I just extruded that similar to when we divided it all the way through, and then I just divided it kind of like what we did previously. In this case, there's going to be 5 excavations. The other thing is we brought in piles, which those can just be drawn from points directly on any location, or even you can even draw them by coordinates or by table. And then you can extrude those to make lines. So we have piles in place. And the last thing you'll notice is we have the raft on which the structure sits. So in this case, the coordinates matter. The raft is always, even in our previous model, right at 0 in terms of the height and the z-axis. And the structure that was made in the MIDAS gen was also at the origin. So that makes it line up easily. We can move things around within the program, no problem. And the last thing would be, in order to make it match, is we want to draw some points and then imprint them into the solid face. So what you would do is you can move this work plane around here in the work tree. So because the raft was already at the origin, turning this work plane just to the XY coordinate system is already matching. And then I would just be able to draw some points directly. The program allows me to automatically select, like in this case, nodes from the structure that was imported. The structure is already meshed. So I would do that for the base. I would just go and click to make a point at every single node of the base. And then once the points are in place, I would use this command here called imprint. It's very similar to AutoConnect, except it's for one, I guess, like point or curves. So I would tell it like, I want this face to have these points, imprinted on them. And that will give me this basic geometry that we have here. So now that when I mesh the raft, the nodes will line up perfectly to it. So we have our geometries. The building itself is already meshed. So I'm going to deactivate that. And what we want to do now is, again, import the materials from a final file. These are all the sections from the building that were imported, but we still need to import what would be the materials of the soil layers and the tunnel and such. So here I'm importing these, including pile interfaces, pile sections. We go to OK. I don't need to bring this in again since I already have those. Notice the tunnel in this case, as I mentioned, is not a solid anymore. It's going to be a 2D shell element. So you give it a thickness to the shell. And the pile is a 1D beam element. And that we have a database that you can select from. This is a very simple shape. It's just a solid round pile, but if you were to choose some other kind of structural section, we have a pretty big database that you can select by different standards. It's almost, basically it's the same database that we have in our structural program. So we have everything in place and we can proceed to mesh. I'm going to deactivate that. So we're going to go to 3D mesh. We're going to mesh the raft. I'm going to give it a value of 5. This is the raft. And you can kind of see that it's not like in the last case where it was almost like a grid. It's a bit of an unusual geometry. And of course that has to do with the nodes where you put the points to match the nodes of the building. So now if I activate the node number, you can see that for the raft, there's kind of like a pattern to be in the range of the 1000s, but the building was imported first, and that had its own set of nodes, and those are in the lower, in the 60s. So you can see that where the nodes connect with the raft and the building, if I deactivate the building, the node numbers match on the raft. So they're being shared, so it's all connected properly, which is, critical. So now we can mesh the tunnel. I'm going to deactivate the curves and the surfaces. And I'm going to give it a size of 10. And in this case, it's not the structure, it's not a solid tunnel. It's not a 3D tunnel. So these sections that I'm selecting are actually going to be just the soil layers that will be excavated. So I'm just going to give it a material of one of the layers that it's in. Let's just say the soft rock layer. But I'm going to call it excavation. And then I'll proceed to mesh the soil layers. So this is the top layer, which would be sand material. This mid layer, we can say it's weathered rock, but I'll just call it again the mid 1 layer, or whatever you want to call it. This third layer will be soft rock, and I'll just call it the mid layer 2. And then this last layer is hard rock, and it can just be the bedrock or the base. So we're done meshing the solids. What I'm going to do now is I'm going to create the shell walls of the tunnels. So instead of having to kind of try to capture all the element nodes from the meshes of where the tunnel will be excavated, I can actually just do that from the geometry. I can just activate the sections that are going to be excavated, and I go here to extract. And so there's an option. I mean, I could have done it by the nodes, but this option of selecting faces makes it much easier because I can just select everything and let go of the front and back face of the tunnel. I use this option here to skip duplicate faces. Basically, I don't want to make a shell in between these excavations. And here I give it the property of the tunnel. And this is just for the sets. So this will be the tunnel walls. And so now we see this here that we have our 5 sections that we're going to be using for the stages, the sequence of the tunnel being excavated and then reinforced. One thing that we do have to double check though is the names. So we see here the program, it would seem like it was smart and it knew that which way we were going to go, but it doesn't know that I want to excavate from left to right. So for instance, this is tunnel 1, that's fine. This is tunnel 2, that's fine. But then tunnel 3 jumps out to what would actually be number 5. So I'm going to modify the name here and call this tunnel 3. This is now, it's named tunnel 4, but it's actually, oh sorry, this would be tunnel 3. This should be tunnel 4. This should be tunnel 5. And then this will be tunnel 6. And then just similarly do that for the excavations. And you'll notice this in a second as soon as I start defining the construction stages, why it's much easier to keep track of this with the proper name. So similarly, this will be number 6. This should be number 5. Yep. And then this should be number 3. And this will be 4. So now we can keep track of everything much easier when we're defining our stages. The last thing we need to do is mesh the piles, which we haven't done yet. So I'm going to activate here the curves. You see here, this is where the tunnel was drawn initially. We're going to mesh 1D piles. The number of divisions doesn't really matter. So you notice that we've been meshing in 3D by size. When it's 1D elements, it's actually easier just to give it a division since you can directly just see how many times it's going to be divided. In this case, since we're going to add pile interface, it doesn't really matter. So we go here to pile interface. And essentially the interface is going to disconnect whatever, or it doesn't require the pile to be connected to the nodes of the soil one-to-one, since it has kind of like these like springs capturing that behavior. And similarly for the pile tip, it's also like a spring at the tip of the pile for bearing capacity, if that's what you're trying to the type of pile behavior you're trying to capture. So we're done with the meshing now, and we can start applying boundary conditions. I'm going to go here to constraints, and actually for piles, it's recommended that you restrict rotation about the z-axis for your pile elements for stability purposes. So I'll just create this boundary condition on the piles for restricting rotation about the z-axis, and then everything else will just be under the auto constraint, the boundary condition of the rest of the model we see here. And now we can define our construction stages. We're almost done. So we'll go here to construction, stage set. We're going to create 2 cases, the first one being with piles. So we click it, we go to define. And in this case, we want to keep track of what we've been doing. This is everything we have up to this point. And then for construction stages, you have one where you activate data and then deactivate. If I switch this to show me only activated data, it's easier to track. For instance, in the initial case, we know that nothing has been excavated yet. It's going to be everything just like before anything happened. So we start dragging and dropping from left to right. We'll start to see things appear, and that makes it much easier to keep track when you have this option. So as I mentioned, the first stage is just the ground, and we apply the boundary condition, and the only load we're going to include is the self-weight, and that was important, but the program recognizes that as the same self-weight load. So we can just activate that, and we're going to clear displacements. We go to new. In this stage, we're going to activate the structure, which is here in the default mesh set, and we're going to activate all the pile and raft elements. So the raft and the piles, and of course we need to apply the RC condition. Stage 3, we're going to start to excavate. So for that, we just drag and drop, and this is where the name is important since there's a certain sequence that we want to follow. I mean, you can visually kind of keep track of it. If you deactivate some of the soil layers, you could keep track of what's being excavated, but the name makes it much easier. So stage, we excavate first, then we're going to do the excavation of the second one, and in this case, this is where we activate the first reinforcement, the first tunnel wall. Excavate 3, activate tunnel wall 2. Excavate 4, activate tunnel wall 3. Excavate 5, tunnel wall 4. Now, in cases where you have many excavation stages, if like it's a very massive tunnel project, here I'm just going to activate the last 2 walls together for the last excavation just to save a stage. We do have a wizard that allows you to easily set this up without having to manually go, dragging one by one. So particularly handy for tunnel excavations when there's maybe hundreds of excavation stages. You can use this feature, the wizard, to allow you to do this automatically. So what I'm going to do here is I'm just going to make a copy and rename it as no piles, because everything basically as far as excavation is going to be the same. Here I'm going to click modify to change the name. The only difference is that in my second stage, my structural installation stage, which I can go to here, for this particular case we don't have piles, just the raft. So I just leave the building and the raft in place. And so we're done. We just create 2 analysis cases, 1 for each, and we can run this model. So we go here to analysis, general. These are construction stage analysis, and these are the 2 sets we created. So you just give it, 1 for each. 1 construction stage for pile, and 1 construction stage for no pile, and you could run it. For again, time purposes, I'm just gonna open the finished file. That's not it either. Shit. Here. And so what we see here now is in the post processor, we have the 2 sets of analysis, the piles and each of the stages, and then of course I gave them names, and then the case for no piles. And what we can do is just compare. In this case, it's the settlements. We can do, again, the cutting planes to kind of get a better idea. We can ask it to give us a max and min reading, change the units. So this is with the piles, and we're seeing about 115 millimeters, and without the piles, and there's much more settlement on the raft, we're seeing about 140 millimeters. We can use this feature of probes to select elements, kind of give it these tags on the spot. And we can kind of change it around a bit here. And this is handy if with this bar, I can use my keyboard to go left or right in the stages process, right? So this is where the structure is installed, and then we can see here the additional settlement of almost maybe 6 millimeters since the excavation happened. So that's kind of handy using this probe feature. And lastly, I'll show you this feature called extract. If you wanted to use kind of like the same procedure, but graph it and compare it to other results, you can use this extract function. You can tell it what kind of results, for instance, for the pile case, displacement, total displacement. You can kind of tell it if there's a construction process, which stages you want to include, and then you can just select a node of interest, or you can ask it for the maximum or the minimum, and you can create a table. And then you can go back and select a different analysis case. We select the same results, but the node is still being selected, so I can just create another table. And I can now either copy paste this or send this to Excel or graph it internally in the program and kind of have some sort of a comparison of what's happening over time or during the stages. So in this case, I showed you internally how to graph, but you can also just send it to Excel and compare both. And lastly, the program does give you structural results diagrams similar to what you saw earlier in MIDAS Gen. And so you can see it for both the structure and the piles, so shear forces, axial forces, bending moments. So that would be, if I go back here, that would just be here under the beam element forces is how we can visualize those results. So of course, for the case where there's no piles, if I go to beam element forces, it's only going to show me the results for the building, which is similarly or very close to what we saw in the GEM program. And then the tunnel in this case is actually a shell element. So we would go here to shell element forces so we can see what's happening to the tunnel. So you can get your different forces or moments on the tunnel, but you can also get your shell element stresses on the tunnel. So that is the conclusion of this training. You saw a lot of different versatilities of the program, and I hope it was interesting to you.